Alright, Business Cal. So today we're going to go over L'Hopital's rule, and then we're going to talk about income, revenue, and profits. So let's go ahead and get started. We begin with L'Hopital. So first, L'Hopital, what is it? What do we use it for? L'Hopital's rule is something we can use to help us evaluate a limit from an indeterminate form. And note we've already spoken a little bit about indeterminate forms, and now we're going to talk about how to, or a method that we can use to, to solve these. And so an indeterminate form is anything that has 0 over 0 or infinity over infinity. And it can be positive or negative, doesn't matter. But as long as you've got a 0 over 0 and then infinity over infinity. So basically, L'Hopital's rule says if we have something like this, well then we can write it, the same limit as before, but now we have the derivative of the first one, of the top guy, divided by the derivative of the bottom guy, right? So pretty nice. So let's go ahead and take a look at this. Some examples. It also applies for a left or right-handed limit. Also applies if we're dealing for a limit going towards positive or negative infinity. So let's take a look at this one. Limit as x approaches 1. So note that if you plug in 1 on the top, you get 0, right? Because the natural log of 1 is 0, and you plug into the bottom, and you also get 0. All right, so we got a 0 over 0, so we can use L'Hopital's rule. So this becomes the limit as x approaches 1. And so the derivative of this guy is simply 1 divided by x. And then the derivative of this guy is simply 1. And now we apply the limit. Plug it in there. And we get 1 over 1, all over 1, and that is 1. Okay. Not too bad. Let's take a look at this one. If you plug in 4, this guy is 16. 2 times 4, that's 8, minus 8. 16 minus 8 minus 8 is 0. 4 minus 4 is 0. We've got 0 over 0. So we can use L'Hopital's rule, right? You've got to have 0 over 0 or infinity over infinity. Alright, so let's go ahead and apply it. Limit as x goes to 4. Derivative of the top is 2x minus 2. And in the bottom it's simply 1. We simply apply the limit now. We got 2 times 4 minus 2, which is going to get us 6. Alright. Now this one, if you plug in infinity to both guys, you get e raised to the infinity divided by infinity. Well, that's simply infinity over infinity. So we can use L'Hopital's rule. Right? This one was 0 over 0. That one was 0 over 0. And this one is infinity over infinity. So here, let's go ahead and apply L'Hopital's rule. The limit as x goes to infinity. The derivative of e to the x is e to the x, and the derivative of x is 1. So plug that in, we get e raised to the infinity, which is infinity. Our answer is infinity, right? As x goes further and further to the right, your function is going to go higher and higher up. All right, so down here for the indeterminate difference, we have, this setup here. So if we have this whole thing going on, if we end up with infinity minus infinity, this does not equal 0, right? It is, in fact, indeterminate. And the reason for that is not all infinities are the same size. Some infinities are larger than others. Or another way to think of it, if thinking of some infinities larger than others hurts your brain too much, you can think of it more in terms of, well, g of x might approach infinity faster or slower than this guy. So if they're approaching infinity at different rates, then you're going to have a different answer. We don't know how each function approaches infinity simply by stating it, so we have to examine each one. So right here, it should be pretty obvious that e to the x is going to approach infinity much faster than simply x. We're not going to use a picture to prove this, but I am going to use a picture to kind of make sure you know what's going on. Right, e to the x is shooting up really fast, and this is, well, x is down here. Clearly, this is going towards infinity much faster than this guy is here. But that is not a proof. We can't use that as a basis, right? So let's go ahead and do a little work with this one so we can use L'Hopital's rule. What we're going to do is we're going to factor out an x so that we have x times e to the x over x minus 1. Okay? So it should be fairly obvious. If you distribute this x, you'll get the original statement back. Alright. And so now note that this guy here, if you plug infinity, you get infinity over infinity, so we can use L'Hopital's rule. But first, let's go ahead and break it up so that we have the limit as x goes to infinity of x. And then we've got the limit as x goes to infinity of e to the x all over x. And then we got minus 1 hanging out there, right? All we did was just kind of break up the orders of operation. So now you can see right here we can use L'Hopital's rule because that's infinity over infinity. All right, so on the left-hand side we've got an infinity hanging out here. And so we've got the limit as x goes to infinity. Derivative of the top, that's e to the x. Derivative of the bottom, that's 1. Like so. And so this is simply going to be infinity times infinity minus 1. Now if I take 1 less off of infinity, note I still have infinity, because by definition infinity cannot be counted. So if I take 1 away, I'm still at infinity. So that's going to be infinity times infinity. So if I take an infinite number and I add it together an infinite number of times, that's what infinity times infinity means. Well, that's just going to be another infinity. So what is the solution to this? It is infinity. Note that this does go with our intuitive understanding of from the geometry of the graph. Okay. Next one, we're going to try a very similar strategy. And so then we say the limit as x goes to infinity, apply the limit, we get infinity times infinity minus 1. So I took the limit so we don't have to write that again. 1 less than infinity is just infinity itself, so we have infinity times infinity, which of course is just infinity. Alright, that's it, there we go. Alright, and so that is L'Hopital's rule and how we deal with indeterminate forms. Alright, now let's talk a little bit about money in chapter 4.2. Something we've all had experience with, some more than others, I suppose. So what is C of x? C of x represents the cost to produce x total units, right? It's the total number of units that we're doing. So, it's C of 5 would, for instance, be the cost to produce units, whether the unit was a toy, a coat, a car, doesn't matter. Like keeping it abstract right now. Just something that you're making, and it costs something to make them. Shouldn't be too terribly hard to reason through. So what is a linear cost function model would look like this. And it's worth noting, you might be, where do these cost functions come from? And there's very different ways to come up with a cost function. For these linear methods, oftentimes they come up with, okay, what is the highest typically costs to produce something and what's the lowest it costs to produce something on average, and then they just take the median between the two. There are also some more statistical methods used, like regression models. It's not really something we're going to talk about too much in this course, but if you get into a statistics-based course, those statistics are how they come up with a lot of these models. Various schemes to come up with them, but for right now this is a linear cost model. Note that no matter how many you produce, you always have this 33 cost. That is a fixed cost. And then note that this number right here, that cost right there, that changes with how much you have to produce. If you produce 1, it's 100. If you produce 2, it's 200. This is a variable cost. And so you kind of get to kind of tie in with some of your other coursework, because I know you've heard those terms elsewhere outside of simply a math course. So here we got variable costs and fixed costs. And so we want to know what does this look like? Well, no, it's of course just straight line going through like this. That's our linear cost model. So what about a marginal cost? And we're going to come back to this cost model with a marginal cost. What is the marginal cost? The marginal cost is the cost of producing one more unit, right? If you've produced 500 units, what's the cost to produce the 501st, right? You've already spent the money in the 500 units. What's it going to cost to produce just one more? And this is usually on like a per time basis, like a per day, per month, per year, or per quarter, whatever you happen to be working with. And so marginal cost is defined like so. But note this does have a similarity with the derivative, right? The average rate of change. So when you say C of x plus h minus C of x all over h, well, what does this mean, say, if h equals 1? Well, then we've got C of x plus 1 minus C of x all divided by 1. Well, we can just ignore that in the bottom because there's always 1 is always implied for multiplication and division. And note that this is exactly what we have for the marginal cost. And so we say that we can use the derivative to approximate the marginal cost, particularly if we have a lot of data points, right? If you're dealing with, data points for, if you reduce like, 3 to 5,000 units, well, that one unit is pretty small in the grand scheme of things. We can say that the limit as h approaching 0 is a valid assumption. And so that's why we can say this right here. So the marginal cost for, say, this guy right here equals 100. Right, because that's just how much it costs to produce just one more unit. All right, so let's find the marginal cost when the function is found to follow this particular cost function right here. So we've got C of x equals negative x minus 100 quantity squared. So we're going to take the derivative now that we know how to do the chain rule. So C prime of x equals negative 2 times x minus 100 and then the derivative on the inside is simply 1. And so this becomes negative 2x plus 200. And it's worth noting that if you were to actually plot this, this graph would be a square function, and it looks like this. The cost will always be negative. That doesn't really make a whole lot of sense. So let's go ahead and just say this cost function, we're going to add something to it. We're going to say plus 500, so that way if you graph it, it at least makes a sense as an example for a business application. Nothing wrong with the math we did, but just want to make sure we have that in there. All right, so this would be our marginal cost. So if you had been producing, say at the 100th unit, right? What is the marginal cost? Like, what's the cost to produce one more unit when you're at 100? Well, that's going to be negative 2 times 100 plus 200, and that is 0, right? So that would be our our maximum point, right? So let's talk about the revenue. Revenue is the total money generated from the sale of X units, right? Total money generated. So we have the marginal revenue is the revenue generated from producing one extra unit. So, similar example to the marginal cost. As usual, income is revenue minus the cost. Right, the R of X minus the cost function. And a marginal income is the derivative of these two things. So as a quick example, let's find the marginal profit when the cost is found to follow the function. Right here, that's our cost function. Throw a yellow highlight on that. And then the revenue function is right here. Okay, so let's go ahead and work this through. Hold on, looks like we got a typo. I have the revenue function listed twice. Let's go ahead and blurt one of them out. There we go. Alright, so we got a revenue function there. So what is our income function? Well, our income function is simply the our 500 times x minus our cost function, which is negative 100x squared plus 500x plus 1,000. Okay. And so now we're just going to distribute this minus sign. So we got plus there, minus, minus. All right, so we have a 500x minus 500x. Those go away. And so what are we left with? We are left with 100x squared minus 1,000. And so the marginal income is 200 times x. Okay. And so once again, that would be the additional profit for making another unit at that point, right? So if you say at 10, that's when x equals 10, that would be, you know, $2,000 extra dollars to be made for that additional unit. Okay, so that is all we have for the day.